Okay. So what we should do is just look up the log of x. Now we already said that the log function, and we are going to be using the natural log. And we said that this concept of e, the exponential, is actually a number, irrational and transcendental number, 2.71828, blah, blah, blah. We'll probably use 2.718, just like for plot pi, we would use 3.14159. However, you've got a calculator. The calculators will always have e on there, so you don't have to worry about it. The graph, well, here, first of all, let's talk about what the natural log is. And this is going to be kind of an important thing. So I'm going to the natural logarithm on Wikipedia is probably a good idea. The natural log is the power to which e would have to be raised to equal x. So in other words, e to what power equals x? So I'm going to do this. Open up Epic Pen. And all I'm saying is that e to hold on. The natural log of x is e to what power?
E to the x.
Right? So that's kind of what we're defining it. So
There we go.
what I'm looking for is, what are the domain values for x?
Any positive real number.
I can put in all numbers, right? So
Right.
if I plug in 0, what happened? What's the answer?
1.
1.
Actually, you know what? This is... What this should be is over here. Sorry, I'm doing this poorly.
Right.
I don't have some of the things that I want to have. The natural log of e to the x is x. So the natural log and the e are basically inverse functions, right? What we're saying is that if I take e to the power, then I know, and I take the natural log of it, I get the value that I'm looking for. Now, one of the things that you can do, and this is kind of what I asked you to do on the test, and let me go here. Is to look at this for a logarithm. Now, a logarithm is just like a natural log, except the difference is the thing that we act on it is e, as opposed to some other like this. So look at over here at this sentence. It says, in the simplest case, the logarithm counts the number of occurrences of the same factor in repeated multiplication. That's blah, blah, blah. The logarithm of x to base b is denoted as log of base b of x. And you would do that without parentheses. So log 10, you could say, or log 2 of x without the explicit base. The log of x in base 2 is equal to some number. And then what we can do is we can look at this and say, well, it's the same thing as base to the power, which is going to equal x. So if I think about this here, and I give an example, if I say, what is the log of base 10 of 4 equals something, right? I don't know what that number is offhand. But that's the same thing as saying it's 10 to what power is equal to 4. So 10 to some power is 4. Well, the same is true with the logarithmic function. Okay, so except instead of 10, what are we putting in? We're putting in e. E to some power is equal to the natural log of whatever that x is. So when I say the natural log of x, I'm saying that's e to what power is equal to x. Does that make sense to you guys? So what would happen if I took the derivative? That's what's going to be more interesting, is when I take the derivative of these things. So I'm going to go back to where I was before. On the natural log. And before I even start that, is I'm going to look at the graph. So I'm saying over here, what values of x am I putting into the natural log? Well, I can put in any value of x, but when I plug in that value of x at 0, what's the natural log of 0?
1.
1.
Well, the natural log of 0 is like saying e to what power is equal to 1, because here's x equals 1, right? So e to what power is equal to 1? It must be 0. E to what happens when it gets larger than 1? I'm going to say e to some power is greater than 1. Well, if e to the 0th is 1, then e to anything bigger than, when I'm trying to say e to any other power is going to be greater than 1, I must be a positive value. Okay, so x will increase, and it increases, it continues to get higher and higher and higher and higher the bigger x is. But because it's an exponential function, I don't need to increase it as much as I'm increasing x. So I get x equals 8, and y, or the y value, or the f of x, is now going to be just a little bit over 2. Okay? But what happens if I start getting values between 0 and negative, or between 0 and 1? I'm saying, okay, what, here, let me do this for you guys. Oh, rewind, this is what I want to do. If I'm getting a value of x, which is between 0 and 1, that's a fraction, right? Do you agree with that?
Mm-hmm.
So e to what power is going to be fractional? Then what's in the question mark here has got to be negative.
Mm-hmm.
Right? That's got to be a negative value. So the function of x is going to be a negative value. And then the question is e to what value, and I can write it this way, is going to be equal to x when, if this is negative, what if x is negative? Is there anything 2.718 to any power, is it going to result in a negative answer?
No.
Okay, so in other words, the domain of this is going to be 0, numbers greater than 0 really, and then positive numbers. So the natural log of x is going to be what? Of 0. What's the natural log of 0? Take out your calculator and tell me what it is. Or if you have a computer, you could easily just type in.
No.
Undefined.
Yeah.
It's undefined. Because what kind of a graph is this? What is the nature of this graph?
It's an asymptote?
It's an asymptote, right? It's an asymptote approaching 0 but never reaching 0. So the natural logs domain are truly positive numbers. The range is infinite. because you can get any value of the range. It's going to take a long time to get really big values of x. All right, so does that make sense?
Mm-hmm.
Now, in this whole thing, there are some major issues that we should probably deal with. So I'm going to go back here, and there's actually natural logarithmic rules. And one of the things that you're going to need to know and to remember that will make you successful in this class, what color can I use? Are going to be this. If I see, and just to make it easy to write, I'm going to use y instead of f of x. So if I say e to the y equals x, one of the things that you want to do is sometimes you want to get rid of the the exponential notation. So what I can do is I can take the natural log of both sides. So again, this is just simple kind of algebra. Whatever I do to one side, I need to do to the other side. So I'll take the natural log of both sides. But when I take the natural logs of the exponent, that leaves me y equals the natural log of x. Okay? I hope that makes sense to you. So the natural log of x is equal to the log and base e of x, which is a different notation. E is Euler's number, 2.718. And here's, we don't need to worry about that. Let's go to these rules here. And I would suggest that maybe you could cut and paste this, or take a look at this. But these are just going to be something that you need to know. The product rule. The natural log of two numbers multiplied is just the sum of the natural logs. And I think I don't know, where do you guys do this? Is this in algebra or is this in trig?
Trig.
You do natural logs in trig where you actually prove why they are?
I think so. It was 1963, so.
Okay, so for this one here, right, if I took the natural log of x times y, couldn't I just take e to this? And what does that get? And so the other side, we're saying, well, I'm taking e to the natural log of x plus the natural log of y. But when I take two numbers, that's just e to the natural log of x times e to the natural log of y. Right? Because when you are summing up like any number to a power where it's a plus b is just this times that. But I know that this is equal to x times y. And e to the natural log are inverse functions. So the left side is x times y. And then I write QED. You guys know what that is?
QED?
Yeah, it means I'm really smart and I figured something out that nobody else can.
Yeah, do you remember what it stands for?
Latin.
Where are you guys? Wait, I don't see. Oh, there's your faces. It means quo ergo demonstratum or something like that. I have shown what I have set to prove. Thus I have shown it or something like that. But QED is just that term that you'll often say, saying, hey, I did my proof the way I was supposed to do it. Okay, so that's how that one works. Now the same is sort of true, but a little bit more complicated, of the quotient rule. It's the log of x over y is just the log of x times log or minus log of y. So keep that in mind. The power rule, super important. This one, doesn't get any more important for doing well in this class. Okay? It is the natural log of x, of x to the y is equal to y times the natural log of x. Now I bring this up and I say this is super important because it's important that you remember that rule. We're going to be doing proofs in this class. We're going to be doing derivations. The big derivation in this class is the Poisson's equation, which defines what theta is, the potential temperature. And that is going to be required that you remember steps like this.
That one's the power rule, right?
That one is called the power rule. So these first three things are pretty important. Here's a couple of things too. The log of infinity, the log of 1, the log of 0, the log of a negative number is undefined. Those are all things we've talked about. But now we get to the derivatives. And the cool thing about this is you should be able to read this and understand it. And what they're saying is f of x is the natural log of x. So I could write it this way, equals the natural log of x. I'm taking the derivative with respect to x of both sides. This is the same thing as saying f prime of x. And then the derivative of the natural log of x is one that is simply, you need to remember this. The derivation of this one, as I recall, requires to understand how to do natural log in Taylor series. It's a series of numbers. So you do not want to do that. You want to memorize and remember this forever.
So in derivative, it comes down to 1 over x.
That's it. So let's try this one. Actually, to be more specific, James, let's do it this way. In the derivative form, it's really, if I do something like this, but I want to put this up there. So the derivative of the natural log of x is equal to 1 over x times the derivative of x. And the reason I do that is what happens if I said, instead of x, I did x squared. So the derivative of the natural log of x is, or x squared, is 1 over this thing. But this time it's 1 over x squared.
You can't have a denominator that's to a power.
Times
Right?
what? Times the derivative of x squared. So I kind of want you to see this. I'm saying that the derivative of the natural log of this function, it's just going to be 1 over that function. So the derivative of the natural log of this function, x squared, is 1 over the x squared, that function. But it's multiplied by the derivative of that function. Well, the derivative of x squared is 2x times the derivative of
I
x.
think we're in the way.
What did you say?
Am I the only one? We're in the way. The picture,
Oh,
You can actually move it, I believe.
yeah. You can move your guys someplace else.
yeah, now we're getting, wait a minute. Wait a minute. God darn it.
Zoom's
Okay.
a little bit weird, but on top of those things, there's other ways to show that.
But
This,
Paul, doesn't that x cancel with one of the x's in the denominator?
yeah. To finish this up, you are then going to, whoops, I like blue. You're then going to say 2 over x dx. Because this x cancels with one of those x's. Now, we're not going to be doing a lot of this stuff, but this derivative of ln of x is going to be always the case. You're going to see that a dozen times in this class. Okay? Let's go here. So they give a couple of these things. They give a couple of
Can I
derivatives.
ask a question about the derivative of logarithm of x squared again? It doesn't matter how it's used in derivative. Because I don't see dx like in that chart that you had up earlier.
When you have, okay, so what I'm saying is that derivative of some function with respect to x, right, is equal to, I don't know, some new function. But if I said I could multiply, I could say just the straight derivative of f of x equals f prime of x dx. You're treating this like an algebraic property where I could just say the derivative of x times whatever the derivative of that. In other words, whatever that is changing by. That's where that extra thing comes from. All right, let me go here. So that's not bad. So now we go back to our math worksheet. Where's our math worksheet? Oh, my math worksheet's over here. And we get some ideas of how to finish this. So if we think that the natural log of x from a qualitative standpoint looks like this function, right? Then what's the slope of this thing doing? The slope, as it's asymptotic, is approaching 1 when the values are really small or reaching undefined. Then they become a slope of 1, and then the slope becomes closer and closer to eventually 0. Which makes sense if the derivative of the natural log of x is 1 over x. Because when x is close to 0, this is getting infinitely huge. When x is 1, the slope is 1. When x gets bigger, the slope gets smaller and smaller and smaller, approaches 0. So it becomes, by the way, this becomes asymptotic where?
Infinity?
Do this. Right now, take the natural log of 5 million.
$15.425.
Take the natural log of 5 billion, 15.425.
$5 billion is 22 point.
So do you see how slowly this is growing? So you're going from 5 million to 5 billion and you go up by 7. That's almost a flat line. So it's infinite in some weird sense. Doesn't reach an asymptote, but boy, it's going to get there really slowly.
Should we put down the integral rules and the other rules from the list of rules that you showed us earlier?
Yeah, I would do that.
All right. Let me go.
Okay, so we go back to our sheet. Let me put you guys over here for a second. We go back to our sheet. I can delete all of these things. And then I discussed that one. I think that was the last one that we had done. Whoops. That we had done on this. Oh, shoot. That's why. Oh, I can draw on this without opening Epic Pen, can't I? I always forget that. I'll use the mouse. So that's that math worksheet. How does that feel for you? Do you have it nicely written? I'd like to see the quality. What I'd like to do is I want to see the quality of your work. Has anybody completely done this worksheet?
Yes.
James, would you be willing to share your screen and show it to us?
Okay, let me see if I can figure this out.
Let me do this because I think I can. Oops, I don't want that. I want. Go ahead. You can share your screen now.
How's that?
See, look at that. That's beautiful, right?
I used Excel to draw the graphs.
Did you really? Oh, that's cool.
Yeah. It's pretty powerful for doing just simple graphs.
It's not so powerful for doing weird graphs. You know what makes it really difficult is to try to switch the independent and dependent variable axes. Really
Yeah.
hard to
Yeah.
when you do lapse rates, it's hard.
For
So
hard
this
stuff, I
is
use
really
MATLAB
great,
or
right?
Octave. Pardon?
This is really great stuff. So I'd like to see everybody have in your notes, this should be included in the notes that you're going to be turning in to reference what we talked about. So nice job. Go ahead and give me control to share again.
And I do that how?
Just stop sharing.
Ah, there it is. Okay.
Thank you.
Welcome.
I'll go back to here. All right. How you doing, Allison?
Is there any other Excel-like program that you can use for that?
Well, what you could do, James, is you could just go to Wikipedia or any of those math things, type in the graph, and insert that image. Right? You could do it as an image as well, so that would be fine.
Alrighty.
Okay, now there's another worksheet here where we're talking about this chapter. So this is your chapter 1 worksheet. I'm not going to worry about 1, 2, and 3. That's going to be turned in, so I'll grade you on that. I don't think I need to, unless you have a question on this. And then I said answer problems 1.6. Do you have any, have you done this yet?
Yes.
Yes or no?
Yes.
Yep.
Do
Yes.
you have any questions on that?
No.
What did you say for A?
1.6a.
Yeah.
Surface pressure is at the Earth's surface. In some areas, the surface is below sea level. Hence, one would expect that the pressure to be below the sea level pressure.
You mean above sea level? Some, right? So when
Okay.
we talk about 10,013.25, that's sea level pressure.
Right.
But there's a lot of ground on the Earth. Like 70% of the Earth is covered with water, but 30% is ground, and 30% is much higher in the atmosphere. So when I look at the weight of the atmosphere, it's 980 millibars on average. Now you look at Iceland or Greenland, that's 10,000 feet above sea level. So when you look at how much air there actually is, you want to think about that in terms of 980, not 1,013.25. So if I flatten the Earth, I would have an average of about 980. And that accounts for mountains and all that stuff. Does that make sense? Okay, figure 1.6 represents, oh, that's cool. Do you guys know anything about this? I'm gonna share with you this, just because stuff is cool. I'll show a quick video here.
I cannot hear that.
It's a little quiet, yeah.
Okay, what did you say? You couldn't?
It's quiet.
Yeah, cannot hear it.
Anybody else hear it well?
Very little.
Nope, can't hear it.
Okay, well, let me go back and just say that what Lorenz did is he took just simple equations on a forecast, and it was an old computer. This is a long time ago, so look at this dot matrix printer. And he's saying, here's a value of X, here's a value of Y, a value of Z, right? And he's just doing this computer programming. And when he did a program, he let it run over the weekend because it took a long time to do that back in the day. And then he got some answers. And then he did something and he ran it again, and he realized he got completely different answer the second time he ran it. And what he ended up doing was he had rounded way out someplace. Some value he just rounded off. And he got completely different answers. So this is where the idea of chaos theory came from. Let's see if I can make it. So what you're saying is that he figured out this way of doing an analysis by changing the points that you give, the exact values, the precision of the initial conditions. So he's applying different, he's using different points to start based on these equations, and they all tend to focus around these 2 points. So no matter where they start, that's what all these dots are. Watch what happens. No matter where you started, they all go to these things called a strange attractor. So they're saying they all follow their own path around each of these points, these attractors, without intersecting. It's pretty cool. If you just have a chance, you can look at that a little bit later. There's a whole lot on there. But that's what this thing is on page 6.
Benefits such as unlimited doctor visits, specialist, emergency room, hospitalization, surgery, vision, dental, and
Okay, so that's that. What else do we have on this one?
What are the 3 dependent variables that Lorenz had? I couldn't figure that
I
out.
think he was doing temperature and a horizontal. I mean, it's probably X, Y, Z and temperature and time. So that he was doing a temperature forecast, as I recall. Okay, so now the next one, it says, in equation 1.1, y is dx dependent on cosine of theta. Okay, so now let's take a look at, nail down into here. So you're on page 4 of the book, and you're looking at the zonal velocity. So reading the zonal velocity, let me do this. Reading the zonal velocity, it says that u, and you need to know that u is the zonal wind. It is the component of the 3-dimensional wind vector that goes east and west only. Positive u is to the east. The east. And it's, what do the 3 lines mean?
All is equal.
No. Wait, we've done this in some of my classes. Do you remember what I used 3 lines for? It's defined as. 3 lines means it's defined as. So we are saying we are defining the zonal velocity as the change in dx dt.
That's a question.
And what is
That's
the
a
question?
What is the name for that?
How does the top number change in relation to the bottom number?
With respect, well, what is, but in dx dt, James, what is it?
X over t, that would be, how does horizontal distance change over, or temperature change over
See, I knew
horizontal
you were going
distance?
to say that. What's wrong
The
with what
grain-
you said?
The Grangian rate of change.
Lagrangian?
Lagrangian, thank you.
No, but
You know what I was talking about.
you guys, dx dt,
It's a question.
how does,
It's the rate of change with respect to time.
well, no, but how do you say that when I give you the derivative, I told you, you need to know how to say it. How does x change with respect to t? What is x?
Distance.
Zonal.
No, x is not a distance. What's x?
Displacement.
No. Ah! Those of you who've had my classes, Bruce, you know what x is.
Yeah, I thought it was distance, so I'm
See,
not
this
good
is
at
where you guys, oh my God, I got to stop you from this habit. Allison, what's x?
I don't know. I just woke up.
Operator.
What does x on a treasure map tell you?
Location.
That's a spot.
It's your location. It is a location. How does your location change over time? But now we have to be more precise. It's not just a location. It's a location on what we would call the x-axis, which is the zonal axis, which means as I go east and west. It's my east and west location, which would really be what? What is the east and west location on a globe called?
Longitude.
Longitude. Right? That's what longitude is. So dx dt is how does my x location change with time? Now, everybody, a change in location is a distance. But that's not what the derivative is saying. It's not the distance that's changing. It's the location that's changing. Right? So if I did this, if I go dx dt, that's how does the location change? How would the distance be? The distance is a second derivative. It's the derivative of the distance over time.
Yeah.
That's the change in the distance. I mean, this, we're not going to notate it that way, but that's just the thought process. And I always tell my students, I'm like, hey, where do you live? How far away do you live? And you say, well, I live 5 miles away. No, I live 6 miles away. That's a change in the distance. But your location is X. Now go to the second one. What is Y or V defined as? What's V?
It's a vector.
What's little v here?
meridional velocity.
Meridional velocity. And that is defined as the change in y, dy dt. In this case, that's a question. How does your y location, your location on a globe as you move north and south? But when you move north and south, what are you changing?
The latitude,
Latitude.
You're changing your latitude. So what's that letter?
V.
D what? What is that letter? What's that
Phi.
Greek letter in the second equation on page 4?
Phi.
Phi, or I always say phi, right? 2 omega v sine phi, this is change in the latitude. So my latitude changes. Now, on a globe, I want you to think about this. Here is here, I can do it this way. I can draw good circles, but this can draw better circles. Okay, so there's my globe. When I'm traveling north and south on this globe, I am traveling this way. But what I'm really saying is I have a triangle that looks like this. So what is this angle here? That angle is phi.
It's
So I'm
feet.
saying, if I change phi, what's the unit of phi? D phi dt, what's the unit?
Degrees.
D phi dt, what's the unit?
Degrees.
You're only halfway there.
Degrees over time.
Right? Degrees per second. But do I like degrees?
No.
No.
What do I like?
Displacement.
Meters.
Miles.
No.
Radians.
Radians per second. Why radians? Why is radians a better unit? Why do I use radians rather than degrees when I'm doing math? You guys know?
Easier number to use. So I could think it's.
I mean, I can use, like, that's a 30-degree angle, but why don't I use degrees? And why do I have to put everything into radians when I'm doing calculations? A radian is not a unit. A radian is not a unit. 2 pi is a number. We say radians because we don't like to say 2 pi per second. We go 2 pi radians per second. We just throw that in there as a number, as a.
Scalar.
It's like hertz. We don't like to say that's rotating at 30 per second. 30 what? Whatever. So we have radians per second. Degree is a unit that needs to be, like when you're multiplying through, you have to deal with degrees. So when I'm doing d phi dt, I always need to go to radians divided by seconds. So in other words, d phi dt is radians per second. That's really the unit. It's just a per second. But is that a velocity? What's the unit of velocity?
Meters per second.
Meters per second. So I need to know what meters is. Well, if the Earth were smaller and I was going 1 degree of latitude in an hour, and the Earth were smaller, do you understand I'm going a smaller distance? If
Yes.
you're traveling 1 degree of latitude in an hour, right? 1 degree of latitude is equal to 60 nautical miles. And that's equal to 1 minute of latitude. So that's why we use nautical miles rather than statute miles, because we take a globe and we break it down into latitude or into degrees. And we know that 1 degree of latitude is 60 nautical miles. And it's always 60 nautical miles, because all my latitude lines are what? What's another name for latitude lines?
Chords? No.
What's another name for latitude lines?
Strings.
Korean War was fought over what?
Parallels?
Parallel.
Meridian?
The parallel, right? There's parallels. So all these lines are parallel. And so anytime you change 1 degree of latitude, you're going 60 nautical miles. You are going, and if you went 60 nautical miles in 1 hour, oops, 60 nautical miles in 1 hour is going 60 knots. That's why when you're traveling in airplanes, Mike, you know, you're using knots, nautical miles per hour, because that makes more sense when you're traveling on a globe, because now you can measure units of latitude. I'm doing something wrong here. No, I'm doing something right.
Where does the theta come from in cosine of theta if we've got
Okay,
phi
well,
as an angle?
here's that. Well, what you're saying is that's not cosine of theta. You're saying that's the cosine of phi in the first equation, right? Cosine of phi. So now let's do this. Let's go ahead and get rid of this. And let's go to our globe and think about lines that are here. How do I do this? These are longitude lines. So what is this longitude line here? And what is this parallel?
That's 0.
That's the equator, right? So notice that if I went between, let's say, 1 degree of or 10 degrees of longitude here. So I'm gonna say this is 10 degrees of longitude there from here to here. Now at the equator, that 10 degrees of longitude change, and we use lambda for longitude. So phi is latitude, lambda is longitude. That 10 degrees is the same thing as 10 degrees of latitude. But notice when I'm closer at much higher latitude, let's say up here, and this is still 10 degrees of latitude. From there to there is still 10 degrees of latitude. Right? That's still 10 degrees. Do you see that the distance is much smaller? Mm-hmm. Well, what if I'm at the North Pole? 10 degrees of latitude is how much? How far?
Infinitely small?
Well, it's 0, right? If I'm at the North Pole, I can turn 10 degrees of latitude and not go any place. So to change my longitude is a function of the latitude that I'm at. And it's this, so in other words, I'm going to say the change in the longitude is the same as the change, as the change in the latitude at the equator. Right? But the change in the longitude is 0 at 90 degrees. So I want to multiply a function where when I'm at 0 degrees, I'm multiplying by 1, and when I'm at 90 degrees, I'm multiplying by 0. Well, what function does that? And the answer is the cosine of the latitude. Phi is a hard letter to draw. You know what? I think I need to do this. Cosine.
All right, just to make sure I got this written down right here, can you go over that one more time, please?
Okay, so what I'm saying, James, is when you're at the equator, a degree of longitude and a degree of latitude are the same. When I'm at the North Pole, the degree of longitude is 0. There's no distance that I'm physically traveling. So I need to multiply by some function that when the degree is 0, that function has a value of 1. When I'm at 0 degrees, that function has a value of 0. Well, guess what? The cosine does that.
Okay.
So if I were to do something like this, let me go here, and I'm going to look at a lat-lon globe. I should be able to get an image for that. What would be a good one? Yeah, here. Do you agree on here that near the equator, I've got nice squares?
Yes.
When I get to higher and higher latitudes, these squares are not squares. They're very rectangular. A degree of latitude is always a degree of latitude, but a degree of longitude is getting much, much smaller. Just so you understand the implication of this, if I look at a satellite picture, and I look at a global sector of satellite on the full disk, right? And over here, I do overlays, and I want to do, hold on, let me move you guys up here for a second. I'm going to do mapping, and I do latitude, longitude. You see that we've got nice square stuff, right? But when I go to continent, do you see that this projection of the map is got a little bit of curvature, but it's not the same. Look at these squares are not getting a whole lot narrower the further to the north I go. I see a little bit of curvature, but you see that there's going to be a distortion. So if I go to continental, or if I go to global and I go, well, let's look at this, I'm going to see somewhat a little bit of a distortion, but not a lot of distortion. But what happens to the satellite when I'm way up there? Look at what happens when I do 1 kilometer sectors. No, let me go to sub-regional sectors. When I'm near the equator, look at how nice that looks. Looks like we have a tropical storm forming out here. Well, by the way, how did I see the tropical? Is there a tropical storm? What gives me away that this is going to be something worth caring about? Look at this band.
The shape, isn't it?
Band here.
Yeah.
There's strong divergence here as this band's coming out. Sorry, I got a little ADHD there. Looks like it's really going to come out here soon. 80% chance in the next 48 hours. And looking at that structure, I'm like, yeah, that's pretty impressive. Anyway, the point is, look at how nice everything looks. You see how the satellite imagery is very clear? Good resolution. Because when I look down at near the equator, little squares, 1 kilometer by 1 kilometer squares are not distorted. But if I use this and I go up much higher in latitude, to let's say over here, do you see that I don't get the same amount of detail? And that's because those little squares are being stretched out in order to make this look more like a full square. They should be really small. The resolution is going to be poor. So we're actually remapping a projection of a map onto this. And our data values way high to the north and way far away from where the satellite's looking is not the same amount of resolution as you are when you're over the equator. So you ever want to see good spatial resolution, you want to go close to the equator and you're going to see things really well because there's no distortion when we remap it. Okay, it is a, hold on. It is a 2 minute. All right. So
I just wanted to make sure I wrote this down right. So when you have the latitude, I want to make sure I got this right. Latitude is represented by the not lambda, the other one. God,
Phi.
these words.
phi.
Thank you.
Phi.
So when phi is 0 at the pole, and lambda is 1 at the equator, right?
What?
That's what you use to.
Okay. What I'm saying is that when I'm at the equator, a degree of latitude and a degree of longitude are the same distance. Okay,
Yeah, I get that.
Okay, so I'm saying when I'm at the equator, phi is 0, then the change in the longitude is the appropriate distance. It's the correct distance. You can convert those degrees into nautical miles. When I'm near the pole, when I'm high latitudes, where phi is up in the 85 to 90 degree range, then the change in the longitude is a much smaller distance. So it's not the same distance. It's not like 60 nautical miles for 1 degree of longitude. I need to multiply it by something whose value is going to be a lot closer to 0. And that's why I use the cosine of phi. That's why that first equation has RE, the radius of the Earth, times the cosine of phi. And when the phi may be a unit, degrees are units, but when you take the cosine, it drops the units. So there's no unit. You have radius of the Earth, which is 6.37 times 10 to the 6 meters, which is the unit, times the change in the longitude. So if I'm traveling east and west, I could say, here, do this problem. How fast am I going if I change my longitude 1 degree per hour? How fast am I traveling?
60 nautical miles.
Wait a second, you have to ask me a question.
Where are you?
Where am I? Okay, we're at 42 degrees latitude. So at 42 degrees latitude, what is your velocity, your zonal velocity, if you're changing your longitude by 1 degree per hour? So go ahead and do that. And now we're going to get into break your habits. Okay, do you have an answer? That's a bore. I'll have, next time I do a problem like this, I'll have to go Alt P and pause. You have an answer?
No, I wasn't
Okay,
doing it. I was
I'm
doing
going to show
something.
you how to do this.
Okay.
Let me share my screen first. All right, and let me find, where's my Epic pen? Epic? There's Epic pen. Where are you? Oh, there you are, Epic pen. Blank screen. We'll trash this. So you want to, when you're doing work, you want to set up your problem nicely. Okay, so you're saying, my change in the longitude is 1 degree. The change in time is 1 hour. Okay? And we are looking for the velocity, which is u, which is RE times cosine phi. And we said we said the latitude was 42 degrees. And we also want to say that's the change in the longitude over time. So, right, we say, when I do my problems, and we did this in intro, this is how you do a problem. You write down the governing equation. Then you write down what you know. And then you plug in. But you should write down what you know in scientific notation. And you should also write it down in correct units. So this is going to be a little bit of a change. So now I'm going to go to more calculus and say, what is d lambda is equal to 1 degree. But 1 degree is actually 2 pi radians divided by 360 degrees. But for simplicity, I might want to change that even to make it pi over 180. Okay, so that's, the degrees cancel out, and so I'm left with pi over 80, or 180. Because the degrees cancel, right? Are you getting that concept? The degree is a unit, and the degrees cancel. So I'm converting this into radians. Then I go, well, wait a second, what's my dt? It says equals 1 hour. But is that what I want? What is something called SI units? If you will turn in your book, for those of you who have the book, I want you to turn to page 467. And yeah, that's fine. 467, 468. This is an appendix in your book that you need to have many, many times. So you're going to have universal constants. You'll need to know a lot of those constants. You will remember them the more that you use them, but you'll have access to them. But if you go to page 468, it says units in conversion. This is what we call SI units, and everything you do should be in SI units. International standard. It's a French word. Standard in whatever it is. So what this means is, what are the units for degrees? What's the international unit for degrees? For temperature, I mean.
Kelvin.
It'd be kelvins, right? Now, meteorologists are well known for saying degrees Kelvin, and I don't have a problem with that because I grew up in that environment. You talk to any physicist and they'll go, no, you can't do that. You have to say those are kelvins, not degrees Kelvin. And I
Or
go,
Ron.
Chemistry will tell you the same thing.
they'll say degrees Kelvin?
We say Kelvin.
Oh, yeah, and that's the correct thing. You should just be saying Kelvin. We're meteorologists. We do everything in degrees, but whatever. What's the standard unit for distance?
Meters.
Meters. What is it
Meters.
for? What are the ones? Time.
Seconds.
Seconds, right? So we want things in meters. We want things in seconds. We want things in kelvins. All these things are going on. So I'm going to put you guys back in your corner. Get off my screen. Okay, and then I'm going to say, so I need to get this into seconds. So how do I get this into seconds? What can I multiply by?
60 and then for minutes, and then you multiply that by 60 seconds per minute for 3,600 seconds.
60 minutes per hour times 160 seconds per 1 minute. So what am I multiplying by? What am I multiplying inside here? What is this? What is this number inside the circle?
60.
Minutes in an hour.
No. What is this number inside the circle?
1.
Button,
One.
not.
What? No. Inside the circles, those are the values 1. I am using the identity property of multiplication to do this. 1 hour is still times 1 times 1. But now in this case, I'm going hours goes away, minutes goes away. What's the only unit left? Seconds. So if I do that,
3,600.
let me get my black. It's going to be, whoops. It's going to be equal to 3,600 seconds,
Right.
which is really 3.6 times 10 to the third seconds. I also want to know what RE is. Remember what I said, RE, the radius of the Earth, is 6.37 times 10 to the 6th meters. That's a number, if you look on those pages I just told you to look at in the appendix, it says on page 468, Earth and Sun, radius of the Earth, 6.37 times 10 to the 6th meters. Okay, do I have everything? And I said my latitude is 42 degrees. Do I have to convert that to radians?
Depends what your calculator takes.
Well, no, but I don't need to, because if I'm going to take the cosine of this,
Cosine, yeah.
your calculator should be in degrees, probably. But remember, it goes away. So now, there's my problem. Then I go U equals RE cosine phi plus d lambda dt. Oops, I'm sorry, not plus. Times that. And then I go equals, plug in 6.37 times 10 to the 6th meters times cosine of 42 degrees times pi over 180 all over 3.6 times 10 to the third.
So 3.6, that's lambda, right? All right, what like, they can't read the 3.67. Is that x18?
Pi over 180, that's this. We just did that. D lambda is pi over 180.
I'm sorry, not that part. The
Use your
the
words.
first part, I just The first segment of the equation. I can't actually read what you put down there.
What, this?
No, below that. My eyes are not working very well today. Allergies are making it
Well, neither is your
watery.
mouth. What are you saying?
6.37. I can't read the next symbol.
Times 10 to the
Times 10 to the
6th.
6.
Okay.
That's the radius of the Earth, right? Here, you need to think, if you need to think in color, do that. That's this. This is that, and this is that.
So are the final units going to be meters per second?
Well, yeah, let's take a look at this. What are the units that you have in here? You have meters in the numerator and seconds in the denominator. So whatever this is meters per second. And I want you to think that meters times s to the minus 1 is the correct way to write out your answer. Now, go ahead and now calculate that out.
.95
What is
meters
it?
per second. Or 22.
22.95 meters per second. Which you take meters per second, double it, and that's knots. So you're going about 46 knots. So if I'm going 1 degree of longitude in an hour, I'm going about 46 knots, which would make sense because if I were at the equator doing that, I would be traveling 60 knots. Because on the equator, 1 degree of longitude is the same thing as 1 degree of latitude, which is 60 knots in an hour. But other than the fact that this section should go underneath it, and you should be able to make it neat, I'd really like to see you start getting into the idea where we write the equation, you write down what you know in scientific notation, you rewrite the equation and plug in, and then solve. 5-step process. Write the equation, write what you know in scientific notation, isolate the unknown. In this case, you know the unknown was the same thing. Then you plug in. You guys probably have a lot of scribble with just trying to figure out the answer. I want to see procedure. Process is important. Fair enough? Any questions on this?
Could you repeat the 5-step process? Write down the equation,
Write down the equation. Second one is write down what you know in scientific notation. The third would be isolate the unknown. The fourth is when you plug in. So in other words, guys, generally speaking, you want to plug everything, you want to put everything into its order, ready to be solved once you plug in the values. Plugging in the values is the last step before you solve it. Don't plug in the values too early. That's just good procedure.
Oh, wait. Okay. I totally think I figured out the question I had earlier. All right. We're good.
Okay. Any other questions? Let's get rid of that. Let's go back to our math sheet. Am I recording?
Yes.
Are you sure? Does it say recording?
Yep.
Okay. So there's and now your vertical velocity, the last term. Notice they say W is defined as dz dt, which is nothing more than the change in the radius, because your radius is 6.37 times 10 to the 6 when you're on the surface, and then you go up, you're going on a radius change. So those equations, 1.2, those are saying we're looking at the zonal, meridional, and vertical velocity in polar coordinates. spherical coordinates. Okay, by the way, here's what we were talking about. I'm going to click to follow this link. Here's your International System of Units. There's your basic units: meters, kilogram for mass, seconds, amps, which we'll never use in this class, kelvins, moles, and luminous intensity, candelas, which I've never used. But that's just me. Then they have what they call derived SI units, which obviously area is meters squared, volume is meters cubed, speed or velocity is meters per second, acceleration is meter per second squared, and really it should be m times s to the minus 2. Volume or density is going to be kilogram per meter cubed. Then there's going to be derived quantity. Now this, I would suggest, is something that maybe you should think about, but I don't want you to just see it here. If you look at, there's a lot of stuff in there, it'd be a little bit too much. So let's just talk about some of these units. So let's think about equations that you need to know. Force equals what?
Mass times acceleration.
Right? That would be what you should know. Now we know the units: kilograms times meters per second squared. And we call that a Newton. These things you probably should know. You may not know them, but I just want to make sure you have that. What's Greek letter is that?
Rho.
Rho.
Which stands for what?
Density.
Density.
Which is defined as?
Area.
No.
No, not in that area. The
Kilograms.
volume times mass, I think. God, my brain is not working today.
Yeah, I know. Kilogram
Per meter cubed.
Okay, that is the unit of density. What's pressure defined as?
Pascals.
No. What's it defined as?
The weight of the air above you.
No, well, formula. I'm expecting all of you guys to know these things. This is not something new.
Density.
Mm-mm.
Know this.
You want the other formula.
Force
Force over area. That's what pressure is.
Area.
Force.
Mass times gravity. Oh, force
Newton.
area.
Area is meter squared, so pressure is a Newton per meter squared. But a Newton is a kilogram meter per second squared times per meter squared. So what does that equal?
Pascal.
Well, no, but what's the, simplify this.
kilogram.
Newton.
Times second squared, or a kilogram over second squared times meter.
No, not times meter.
It's on the bottom.
Oh, second square.
For me.
Meter to the
That's
negative
right.
1. Seconds
Oh.
to the negative 2.
Okay.
I mean, that would be standard, the way that you'd standard notate this. Remember, the meters, one of the meters cancels out. So you get kilogram per meter per second squared. That's really important. They call that a Pascal. So PA stands for Pascal. So that's just something. So there's a little joke I want to tell you. So Einstein was playing hide and seek with Newton and Pascal. And Einstein goes, okay, I will seek you first. And he starts counting to 10, and they all run away to hide. And Pascal goes, hide somewhere. And Newton just stands there, and he writes this little box, little square on the ground in a piece of chalk, and he stands right on the box. And Einstein goes, 8, 9, 10. And he opens his eyes and goes, this is very easy, Newton, I found you. He goes, you didn't find me. You found Pascal. I'm a Newton per meter squared.
Ooh.
Okay, so that's what a Pascal is. Now, something that's important, because what do we use for pressure? Generally speaking, we
Millibars.
use
Millibars.
That's the relationship. But do you agree that that's also 10 squared pascals? 10 squared has a prefix. You know what the prefix for 100 is?
H.
Hecto.
Move my thing there.
So 1 millibar is a hectopascal. When you look at any writing in any journal, you will see this, like 1,000 hectopascals. And that's what it is, HPA. That is exactly the same thing as 1,000 millibars. Because we're used to these numbers, and they say hectopascals. I say, why do you say hectopascals? Why don't you say millibars? It's stupid. But when you're doing a problem, what do you need to do? You need to convert it into SI units. If you're going to do a problem and solve a problem, you need to put everything into SI units. So Bruce, remember I said put everything in scientific notation? You need to add to that in SI units. Okay, you can always go back and grab this screenshot. You know, you don't have to write everything down. If I'm writing it, you can just go screenshot. Now let's try this. What is work? What's the formula for work? What's the formula for work?
Heat times something. Force?
Times what?
Distance.
Distance. And this distance is really what?
Distance.
A question.
What's it really?
Change in location.
Change in location. Remember this? Force equals change in location. So a force is a Newton, which is a kilogram per meter per second squared, times a meter. So a work is kilogram meters squared per second squared. There's your SI units for work. What's power? You know what power is? That's just work over time. So it's just kilograms meters squared per second cubed. Now, we call work what? What is the unit of work?
Joules.
Joules.
Joules. What's the unit of power?
Watts.
Watt. Just remember that's work and that's watt. Okay? So power would be joules per second, which is a watt. Now, do you understand that work is measured in joules? What else is measured in joules?
Okay, so work is joules and power is watt.
Heat.
Gotcha.
Oh,
What else is measured in joules? What other physical term? What?
Oh,
Cape.
capes.
Well, cape is what?
Energy?
Energy. So energy is measured in joules. For instance, kinetic energy, what's kinetic energy? Formula, quick.
1/2 mv squared.
Which is, if I look at just the units, I've got kilograms times meters squared per second squared, which is really kilogram meters squared per second squared, which is what we said is a joule, right? So if you look at kinetic energy, that is a unit of energy and work. Work and energy are the same thing. What is potential energy? Remember formula?
Just mv squared. Damn it.
Gravity is an acceleration, meters per second squared times height. That's kilogram meters squared per second squared. So again, potential energy, kinetic energy are all in joules. You just got to be aware that when you put stuff into your science, your SI units, that makes life a whole lot easier because everything goes. Okay, Allison, what you can do is you can do a screen save, right? What is it? It's Windows button, Shift S. Try that.
I'm on a MacBook.
What?
Oh. How do you do that on a...
That's why I was taking pictures off my phone.
Anybody know how to take a screen? It must be the Apple key times with something. Just do a Google search on it. Mike, are you in a Mac? Yes? Okay. So figure that out. Just Google how to do a screen capture. And then you don't have to take pictures of it. It'll already be on your computer. So
How do you do it in Windows?
Windows Shift S. So watch. I do Windows Shift S.
Then it'll pop up and then you draw a box.
Pop up, right? And then you can just cut it.
On a Mac, it's Shift, Command, and the number 3.
Shift Command and number 3. Okay. So those are your SI units. Is there any other one that we need to deal with at this point? I think we're okay for now. All right, so now, let's go ahead and get rid of that. We don't need this anymore. And so now we're going to define something, which is even more fun. We're going to define this thing called the del operator. This is the del operator. D-E-L. Not the dill operator. That's totally different. If I were to try to explain to you the dill operator, I don't know if I could do that. It'd probably put me in a pickle.
Is that a D or is it the Greek symbol? That's the Greek symbol,
That's
right?
the little partial symbol.
Partial.
It's not the D. My handwriting may be messy, but it should be legible for important things.
I think my handwriting takes the cake for being the worst.
I totally
Mine's
agree.
pretty bad.
You're known, but I'll tell you what, Allison, you impressed me with the work that you did. So You figured it out.
I'll nominate Ron's handwriting too.
As bad?
Yeah.
No, you haven't seen Allison's, trust me. For any science student I've ever had, worst ever. Then you get somebody like Margot who's like printing like a typewriter. Oh well. So the del operator is this gap. So what I can say is I can say del t. And so what that becomes is dt dz. So all you're doing is you're operating, whatever you put in here gets put in here. You just fill in the blanks. So exactly what are these things? Well, number one thing is this is the, what would you call that to be?
Question mark or the
The
entire
whole,
thing?
the whole thing.
Eulerian rate of change over time.
Right. What's another word you could put in there? What you would say is that's the local time derivative. That's the local
Partial.
or local derivative, time derivative.
Partial derivative.
So it's the partial, which makes it local. It means, and Nick, you're right, that's the Eulerian. That's at a point. That's at a spot. This whole thing is known as the three-dimensional advection. Term. So we're talking about the advection. And advection is always velocity times a gradient. Oh, guys, hold on. I've made a mistake. It's been a long time since I've taught this. I have made a mistake. The del operator, and this is wrong, so I'm sorry to fix this. The del operator is just this. That is the del operator. It's only that part of it. What I'm doing over here is I'm actually multiplying the velocity times this.
So the del operator is the 3D advection term?
The del operator.
Never mind.
The del operator is just this stuff.
It's a notation.
When I take the velocity times this, I get this big term, which is a local time derivative, time plus the advection change.
So one difference between the del operator and the 3D advection term is the UV and the W aren't in there.
Right, right.
The advection term doesn't include the operator, correct?
Well, the idea is I'm looking at advection is the velocity. Okay, so in this case, what is the velocity? V times a gradient. Dude, I am screwing this up, but times a gradient. That is advection. Guys, can you forgive me for being stupid?
It's okay. I certainly have no room to
That should
criticize.
be,
That is not in there.
okay.
What I should have done for you, and let me see if I can make this up. I should have said, this is the definition of the del operator. It defines del. When I multiply it by the velocity, I get this term. I get this term.
Ooh.
And there's a reason. This is called the dot product, which we'll get into later. The advection is just this. So this is just the advection. What I then want to say is that this, which we did the other day, is equal to this. Right? That is the definition of the total, this thing called the total derivative. So this is a total derivative, which is Lagrangian. That's this. That is the local derivative, which we were right in saying before. And then this last term is the what? That's the three-dimensional advection term. So the simplicity of this is that the total derivative is equal to the local derivative plus the three-dimensional advection of that term. In specific notation, these are vectors, but we aren't going to worry about that quite yet. But what we're saying is that the total derivative is what's happening locally plus the advection. This is your three-dimensional advection term.
Okay, so what is del t without the
Del t alone,
yeah.
oops, del t is that, right? Because there's the gap.
Got it.
There's
Okay. Okay, so
I put
V is
temperature in
the,
there.
okay, so V, going back down to where V times del T, V is the UVW vectors.
Correct. And that's
Okay.
where you got
Got it.
UVW. And then del is, well, what is this term over here? What is that? James?
A question.
No, Mike. Mike, what is that?
Are you changing temperature over a change in location?
Okay, change in location over a change, change in temperature over a change in location. Or would you also agree that's a temperature change over a distance?
Gradient.
It's not a change in distance, but the change of x is a distance, the change in location.
Change
So in
location.
other words, this is the change in temperature over a distance. What is that called?
Gradients.
That's a gradient. So this is the temperature gradient. What temperature gradient?
Local temperature gradient.
No,
In the X direction.
which is
Meridian.
called,
Oh, in the east-west direction, yes.
which is called,
Zonal.
Zonal.
that's your
Zonal.
zonal temperature gradient. What's this? Oops.
Meridional.
Meridian.
That's your meridional temperature gradient,
Vertical.
and that's your vertical
Last one.
temperature gradient. So advection is always velocity times a gradient. This del is an operator. When it operates on a
Something.
number like temperature, which is what we call a scalar. Do you agree temperature does not have a direction associated with it?
Correct. It's a scalar.
Temperature operating on a scalar is called the gradient operator. That's what a gradient is. Okay, does that make sense? Allison, how's that with you?
Good.
Okay, so I'm going to get rid of this. You can always go back and screen capture off the Zoom. And I'm just going to show you really quickly without getting into the woods about dot products. But what if I took del, let me use black. What if I use del operating on this? Del is actually a vector operator.
You're multiplying two vectors together.
Well, then do you understand? I would go so I'm plugging in the velocity, but the velocity, how does the velocity of something change as you go in the x direction? What's the only change in the velocity that happens while you go in the x direction? Like, here, let me just go in 2 dimensions, makes it simple. And I have a vector like this.
Okay.
Do you understand that this vector is your velocity vector?
Right.
That velocity is equal to u plus v.
Right.
The components.
Right.
The x component, the y component. How does this velocity vector change as I go this way? Do you understand that v's not changing as I go that way? But u is. U is the change in that. So this is the change in the velocity with respect to x, which is only u. So all I do is plug the u, v, and the w in there. So here's the question for you. What is this term?
Displacement.
What is that called?
Is it the zonal
Question.
velocity?
How would you say that question? How does the
velocity change
velocity change with location?
with the change in the location?
and which way is the location changing?
East-west.
Okay, so how does the zonal velocity change as I go east-west? So let's draw an example of one. Let's take a velocity going this way. And then as I move x, this is faster. Do you agree that the change in the u is greater as I move in the x direction, as I go toward the east? That's a positive change. So what's the ear doing?
Accelerating.
You're right, but
It's
There's a
getting
better
increasingly faster.
yeah, but what is this illustrating?
Divergence.
Oh,
Right? That's divergence. And then dv dy says the velocity from the south to the north, as I go to the north, gets larger. Divergence. And the same was true in the vertical. So this, when I take del operating on a vector, that's called the divergence of the vector. Now,
The z
if you
direction
were
would be convection.
negative, so convergence technically is negative divergence. Oh my gosh. We are way over time, but whatever. Here's what I want you to understand from this though, guys, is when you have del operating on a scalar, that's called the gradient. We know that term, right? If you were taking Calc 4 when you did vectors, which is what you do in the last little unit of calculus, is you do this. You call this the gradient vector, the gradient operator. But we know what gradients are because we deal with them in weather all the time. We really know what divergence is. I think most students go, that's called the divergence, it's just a name to them. But divergence is an actual fundamental physical property. Now there's another way to multiply vectors, which we are going to get into at a later point. But just so you know, I can multiply it by this, and that's called the curl. Don't worry about this, don't write this down. That's called the curl. But if you have a curl, what does this look like to you? If I curl my fingers. That's
Right-hand rule.
That's vorticity. You don't know how to do this yet, so we're not going to deal with it. Okay, so you have to keep reading in your book. I want you to read through the rest of chapter 1 for Thursday. And then we'll begin chapter 2 ultimately. But we've done a lot of the math homework. We've done a lot of the math stuff that's going on. So. And that's the end of class today. Whoops. It's end of class. I'm sorry, I didn't mean to go so late. I need to get a clock in my room.